gravitational pull that makes these things orbit. If there were no massive objects, these things would go flying off, or at least go on a much slower rate, because all that determines how they go around is how much mass is inside its orbit. So this is great, because remember, my job is to show there's a lot of mass inside a small volume. So if I know how fast it goes around, I know the mass, and if I know the scale of the orbit, I know the radius. So I want to see the stars that are as close to the center of the galaxy as possible, because I want to show there's a mass inside a small region as possible. So this means that I want to see a lot of detail. And that's the reason that for this experiment, we've used the world's largest telescope. This is the Keck Observatory. It hosts 2 telescopes with a mirror of 10 meters, which is roughly the diameter of a tennis court. Now, this is wonderful because the campaign promise of large telescopes is that the bigger the telescope, the smaller the detail that we can see. But it turns out these telescopes, or any telescope on the ground, has had a little bit of a challenge living up to this campaign promise, and that's because of the atmosphere. Atmosphere is great for us. It allows us to survive here on Earth, but it's relatively challenging for astronomers who want to look through the atmosphere to astronomical sources. So to give you a sense of what this is like, it's actually like looking at a pebble at the bottom of a stream. Looking at the pebble on the bottom of the stream is continuously moving and turbulent, and that makes it very difficult to see the pebble on the bottom of the stream. Very much in the same way, it's very difficult to see astronomical sources because of the atmosphere that's continuously moving by. So I've spent a lot of my career working on ways to correct for the atmosphere, to give us a cleaner view. And that buys us about a factor of 20. And I think all of you can agree that if you can figure out how to improve life by a factor of 20, you've probably improved your lifestyle by a lot. Say your salary, you'd notice, or your kids, you've noticed. And this animation here shows you one example of the techniques that we use called adaptive optics. You're seeing an animation that goes between an example of what you would see if you don't use this technique, in other words, just a picture that shows the stars, and the box is centered on the center of the galaxy where we think the black hole is. So without this technology, you can't see the stars. With this technology, all of a sudden you can see it. This technology works by introducing a mirror into the telescope optic system that's continuously changing to counteract what the atmosphere is doing to you. So it's kind of like very fancy eyeglasses for your telescope. Now, in the next few slides, I'm just going to focus on that little square there. So we're only going to look at the stars inside that small square, although we've looked at all of them. So I want to see how these things have moved. And over the course of this experiment, these stars have moved a tremendous amount. So we've been doing this experiment for 15 years, and we see the stars go all the way around. Now, most astronomers have a favorite star. And mine today is a star that's labeled up there, SO2. Absolutely my favorite star in the world. And that's because it goes around in only 15 years. And to give you a sense of how short that is, the sun takes 200 million years to go around the center of the galaxy. Stars that we knew about before that were as close to the center of the galaxy as possible took 500 years. And this one goes around in a human lifetime. That's kind of profound in a way. But it's the key to this experiment. The orbit tells me how much mass is inside a very small radius. So next we see a picture here that shows you, before this experiment, the size to which we could confine the mass at the center of the galaxy. What we knew before is that there was 4 million times the mass of the sun inside that circle. And as you can see, there was a lot of other stuff inside that circle. You can see a lot of stars. And so there was actually lots of alternatives to the idea that there was a supermassive black hole at the center of the galaxy, because you could put a lot of stuff in there. But with this experiment, we've confined that same mass to a much smaller volume that's 10,000 times smaller. And because of that, we've been able to show that there's a supermassive black hole there. To give you a sense of how small that size is, that's the size of our solar system. So we're cramming 4 million times the mass of the sun into that small volume. Now, truth in advertising, right? I've told you my job is to get it down to the Schwarzschild radius. And the truth is, I'm not quite there. But we actually have no alternative today to explaining this concentration of mass. And in fact, it's the best evidence we have to date for not only the existence of a supermassive black hole at the center of our own galaxy, but any in our universe. So what next? I actually think this is about as good as we're going to do with today's technology, so let's move on with the problem. So what I want to tell you very briefly is a few examples of the excitement of what we can do today at the center of the galaxy now that we know that there is, or at least we believe, that there's a supermassive black hole there. And the fun phase of this experiment is while we've tested some of our ideas about the consequences of a supermassive black hole, being at the center of a galaxy, almost every single one has been inconsistent with what we actually see, and that's the fun. So let me give you the two examples. You can ask, what do you expect for the old stars? Stars that have been around the center of the galaxy for a long time. They've had plenty of time to interact with a black hole. What you expect there is that the old stars should be very clustered around the black hole. You should see a lot of old stars next to that black hole. Likewise, for the young stars, or in contrast, the young stars, they just should not be there. A black hole does not make a kind neighbor to a stellar nursery. To get a star to form, you need a big ball of gas and dust to collapse. And it's a very fragile entity. And what does the big black hole do? It strips that gas cloud apart. It pulls much stronger on one side than the other, and the cloud is stripped apart. In fact, we anticipated that star formation shouldn't proceed in that environment. So you shouldn't see young stars. So what do we see? Using observations that are not the ones I've shown you today, we can actually figure out which ones are old and which ones are young. The old ones are red, the young ones are blue, and the yellow ones we don't know yet. So you can already see the surprise. There's a dearth of old stars, there's an abundance of young stars, so it's exact opposite of the prediction. So this is the fun part. And in fact, today, this is what we're trying to figure out, this mystery of how do you resolve this contradiction. So in fact, my graduate students are at this very moment today at the telescope in Hawaii making observations to get us hopefully to the next stage where we can address this question of why are there so many young stars and so few old stars. To make further progress, we really need to look at the orbits of stars that are much further away. And to do that, we'll probably need much more sophisticated technology than we have today. Because in truth, while I said we're correcting for the Earth's atmosphere, we actually only correct for half the errors that are introduced. We do this by shooting a laser up into the atmosphere. And what we think we can do is if we shine a few more, that we can correct the rest. So this is what we hope to do in the next few years. And on a much longer time scale, what we hope to do is build even larger telescopes. Because remember, bigger is better in astronomy. So we want to build a 30-meter telescope. And with this telescope, we should be able to see stars that are even closer to the center of the galaxy. And we hope to be able to test some of Einstein's theories of general relativity, some ideas in cosmology about how galaxies form. So we think the future of this experiment is quite exciting. So in conclusion, I'm going to show you an animation that basically shows you how these orbits have been moving in 3 dimensions. And I hope, if nothing else, I've convinced you that, one, we do in fact have a supermassive black hole at the center of the galaxy. And this means that these things do exist in our universe. And we have to contend with this. We have to explain how you can get these objects in our physical world. Second, we've been able to look at that interaction of how supermassive black holes interact and understand maybe the role in which they play in shaping what galaxies are and how they work. And last but not least, none of this would have happened without the advent and the tremendous progress that's been made on the technology front. And we think that this is a field that is moving incredibly fast and holds a lot in store for the future. Thanks very much.